Hi, I always liked programming a little bit more than anything else on computers, and for me, programming is just like playing very exciting video game, just having lots of fun doing it. And for that reason, in this video, we will do a little bit of programming in assembly language on Commodore 64, because that can be fun too, right? And I will show you how. And believe me, it will not be hard, so let's begin. Okay, our goal today is to create some visual effects and elements on screen using assembly programming language, but with less code as possible. So that means that we are not going to write any complex routines or write lines of lines assembly code. We will keep things simple, but that also means that we are going to use some of the routines that already exist in Commodore 64 that are part of the kernel operating system or the basic programming language ROM. So let me show you what I mean. So here we have a couple of lines assembly code. Let's run it. And here we go. It's very simple, but still quite interesting effect that we have on the screen. So we will need to read a little bit of documentation about those routines that exist in Commodore 64. But before we start to write any code, we will learn a couple of instructions in assembly language that we are going to use quite often, and everything else we will learn on the fly as we need it. So yeah, let's begin. Okay, so for assembler I will use microassembler that comes in the form of a cartridge, but you can use any assembler that you prefer. So let's begin. Every piece of code that we are going to write today will start with this line. It's 1000x, and this is where we define where our program is going to be stored in the memory once it is compiled. And this is the memory address that we're going to use to execute our little program. So yeah, we'll start with that. Okay, now 6510 CPU, which is in Commodore 64, has 5 registers, but we are going to use 3 of those for number manipulation, and those are A, X, and Y registers. And the A register, also known as accumulator, is mostly used for arithmetics and logical operations, and that is the one that we're going to use the most. X and Y registers are mostly used for some kind of counters, indexing, and stuff like that, but we are going to use those as well. So everything that we are going to do with our assembly code, and basically that's how the CPU works, is just manipulating numbers, and every number has to go through one of these registers. So we have a couple of instructions here that we're going to use quite often, and that's LDA, which stands to load accumulator, and then that means that we can load a number or some value into accumulator. The opposite instruction of that is STA, which stands to store accumulator. So that means that value which is in the accumulator is going to be stored somewhere, somewhere in memory or somewhere else. And here we have also a couple different modes. We can load accumulator with specific value. Let's say this represents a decimal number 64, which is immediate mode. That means that number 64 is going to be stored in the accumulator. We have option to use hexadecimal values as well. So in this case, the hexadecimal number 64 is going to be stored in the accumulator. Also, we can write our number as binary. So let's say 1, 2, 3, 4, 1, 2, 3, 4, so that 8-bit number is going to be stored in the accumulator. Beside this immediate mode, there is also absolute mode. We don't have to use immediate value. We can use memory address so we can load some value that is stored in memory of Commodore 64. So for example, DE. So this is of course a hexadecimal representation. This is how we load value that is stored in this memory address on Commodore 64 into accumulator, and this mode we will use quite often. Also, we can store some value that is in the accumulator to memory of Commodore 64. So this instruction STA will store the value from the accumulator into memory address DE. The same things apply to X and Y registers. So if we want to load some value in X register, we use LDX instruction. Also storing is STX. That means that we are storing the value that is currently in the X register somewhere else. Same goes of course for the Y register as well. Also, there is possibility to move the values between these registers. We can move values from the X to the accumulator and vice versa. We can move values between Y and accumulator, Y register and accumulator. The only thing that we cannot do is move the values between X and Y directly. We have to use a register or accumulator like in between, so we cannot do that directly. The next thing that we are going to use, logical instructions or logical operations. Quite often we are going to use AND logical operation, and the logical operations are always executed on the values that are in accumulator. So we have to load, let's say we have to load some value in the accumulator, and then we have to AND that value that is currently in the accumulator with, I don't know, some other value. So, and the result will be stored in the accumulator. Also, there is OR instruction, and we are going to use, I think, in a couple examples, exclusive OR. The next couple of instructions is going to be about branching and jumping. So quite often we are going to use JCR instruction, which stands for jump to subroutine. And this instruction we are going to use quite often because that's the whole point. We're going to use subroutines that already exist in Commodore 64, which are part of the kernel operating system or basic programming language, ROM. The way how we use this instruction is very simple. We just need to specify the memory address where our subroutine is stored. So for example, let's say DDEF. Let's say that at this memory address there is subroutine. We just call it with this instruction and waiting that that subroutine get executed. And also after our subroutine has finished doing its thing, there should be instruction which says RTS, which stands to return from subroutine. That means that once we call some subroutine, that subroutine get executed, it needs to return to the position where it's called from. So very simple. Also for branching we are going to use B and E instruction, which stands for branch if not equal. Now, how this instruction is used is quite simple. I mentioned before that 6510 CPU has 5 registers. One of those registers is the P, which is status register. And this status register has a couple of different let's say flags. One of those flags is a 0 flag, then we have negative flag and some other type of flags which tell us if some value has reached 0 or something else. branch if not equal instruction uses zero flag, which is just single bit in this status register. So how this works is, let's say that we have some label, let's call it lab1, and somewhere below we have branch if not equal lab1. That means that it will jump to this label every time if the zero flag is not activated. Once the zero flag gets activated, this branch if not equal will not be executed, so it will not jump to the label lab1. It will just simply continue to execute the code below. And this is how we will create our loops. The other way, so this is like a conditional loop, right? And unconditional loop will be using the jump instruction. Equivalent to this instruction would be go to in BASIC. So simply jumping to the label lab1. And what else do we have? And now every program requires some input values, right? So besides some fixed values that we're going to use, we're also going to use some values that change through time, or they are repeatable and that they already exist in Commodore 64, that are part of the kernel operating system as well. So these are like Jiffy clock. So Jiffy clock is simply a 24-bit number that gets incremented 60 times per second. That's about it. So we're going to use that to get some randomness or something like that. Also, we are going to use a raster line counter. And these values are very nice to use for our examples because they are repeatable. The raster line counter is simply related to the graphical VIC2 chip and how the VIC2 chip generates the screen. Those values are changing very fast and they are repeatable. That's very nice for us. We're going to use that quite often. Okay, now we are ready to write a simple and small assembly program and use some of these instructions that I was talking about. And after that, we're going to jump to the documentation about the kernel operating system and the basic programming language ROM, and see what do we have there that we can use to create small demos and stuff like that, some effects and I don't know, some interesting stuff. So let's continue. Okay, now we are ready to write a small program, just a few lines of assembly code. Like I mentioned before, we will start with this line, which defines where our program is going to be stored in the memory once it is compiled. So yeah, that's our first line. And in this example, what we are going to do is simply change the border color. So we're going to constantly change the border color. Now the border color is defined at memory address D0 to 0 hex. So we will load that in the accumulator. That's the first thing that we're going to do. And then we're going to use instruction to add to this number. So we're going to use ADC instruction, which add certain value to the value that's already in the accumulator. So we will add numeric decimal 1. So we will increase the value that we loaded into accumulator by 1. And then at line 30, we're going to store that value from the accumulator back to memory address D0 to 0, and our border color will increase by 1. We'll do this constantly, so we will jump back to this line 10. So let's use jump instruction, and we are going to specify the label. Let's call it a loop. and let's add that label right here. So this is our main loop from line 10 to line 40, and everything in between will be constantly executed. Now, of course, we need to compile this, so I will use assemble operation to compile this, and you can see here that the first line where we define where our program is going to be stored in the memory is exactly that. So our program begins at memory address 1000 hex, and this is the end address, so 1000B. So this is where our program ends. Now, to start that compiled piece of code, I will use sys command. That's the basic command, and I need to specify memory address. Of course, in basic we have to specify that value in decimal, so I cannot say sys 1000. I need to convert that 1000 hex into decimal, and that's 4096. So if I press return, this is what we have. Like you see, we constantly change the border color, and there is nothing that I can do now. This code is constantly running. To stop it, I need to power off the machine and power it back on. So yeah, let's do that. Of course, there's more efficient way to do this. If we need to just increment a value that's stored in the memory by 1, there is a very nice instruction to do so. So instead of loading that value into accumulator and then adding the decimal value 1 and then storing it back to the memory address, we can directly increment the value that's stored in the memory by 1 using an increment instruction. So we don't need this code at line 20 or line 30. All we need is use increment instruction, and this will increment the value that is stored in this memory address D020 by 1. And if I list this code, now we have this. It's just 3 lines of code. Let's assemble it, and again we need to run it, and here we go. So we don't need to do all that procedure. There is some instruction that can make our life a bit easier, like this one. Also, there is instruction to decrement the value by 1. So okay, this is very nice, but the one thing that it's kind of problematic here is there is no way to stop the execution of this code. We do need to find some elegant way to stop this and get back to the basic interface or Commodore 64 interface. So to do so, I will show you one elegant solution. And this is the first time that we are going to use a subroutine that already exists in Commodore 64. I will turn this into the line 30, so now I have this. And this line 20, I will delete it for now, but this line 20 we will jump to certain subroutines, so we'll use JCR. So that's instruction for jumping to subroutine. And the subroutine that we are going to jump to is located at memory address FFE1. Now this subroutine checks whether or not did we hit the stop key. So this is the stop key detection subroutine. In case that we press the stop key on the keyboard, the way how the information is transferred, how can we use it, there is 0 flag activated in the status register, and in that case we can use branching instruction here, which I mentioned before, which is BNE. With this, using this BNE instruction, we will jump to the label loop constantly until the 0 flag is activated, and it will be activated if this subroutine that's located at memory address FFE1 detects that we press the stop key. In that case, the the execution of the code will continue further. We will not jump to the label loop. And in this situation, we need to exit our program in nice way. To do this, to return back to the Commodore operating system or basic interface, we'll use at line 40 instruction return from subroutine RTS. And this is now our code that will do exactly the same like the previous one, except we will be able to stop it and safely go back to the basic interface. So let's assemble this and let's run it again. Same memory address. Okay, we have the same effect, exactly what we need. But now if I press the stop key, we are back into the basic, and this is our code, so I don't have to power cycle the machine every time. So this is very elegant. Okay, now we are going to take a look at the Commodore 64 memory map, because this is where we're going to find all the necessary variables and addresses that we're going to use in our examples. For instance, let's find D0 to 0, which is the border color, and here it is. So let's try to find our Jiffy counter or TI variable, and here it is. So value of TI variable in Jiffys and increases 60 times per second on PAL machines, of course. And we have three addresses defined from A0 to A2, and this goes from the highest byte, because this is the 24-bit counter, and this address 00A2 or just A2 is the one that we are going to use, because this is the lowest byte in that 24-bit counter, and this one changes quite fast, or better say cycles from 0 to 255 quite fast. Of course, when we have two leading zeros in our address, this address is part of the zero-page memory. That means that the I byte is 0. In that case, we don't have to write 00, these two leading zeros. We can just write A2, and that will be just fine. Of course, let's try to find the raster line counter, and here it is. So this memory address we will read and use quite often, and everything else you can find on this page as well. Now the second page that we are going to take a look is C64 ROM disassembly, and here we will find our routines that we are going to use. Of course, I'll put all of these links in the description of this video down below. Now here we have all the routines or subroutines that are used in kernel operating system and basic language ROM that are inside the Commodore 64, loaded into memory, and we can use it if we want to. So let me find here. Okay, and here you can see that subroutine that I've used in this previous example, FFE1, and this says scan the stop key. Now if I click on the memory address, I have small explanation, and for this routine it says if the stop key on the keyboard is pressed when this routine is called, the Z flag or the 0 flag will be set. And this is very handy, so we are calling that subroutine. In case that stop key is pressed, the 0 flag will be activated or high, and we can detect that using any of those branching instructions that will trigger if the 0 flag is high, and yeah, we can use it very easily. Quite nice way to stop the execution of your code. And here we have one routine that is used quite often and says output character to channel FFD2, and here we have explanation of how that routine actually works. This routine will output character to already open channel. One of the channel is screen as well. And this is one interesting routine. From time to time we need to print the value of some register or in accumulator from some memory address on the screen, just to see which number that is really. Also, this is very good example where you can see how we input parameters into the routine, like it's sort of function, and get the result back on the screen. So this routine prints, and it says here, print xa as unsigned integer. Now x and a, x is the x register and a is accumulator. So the value that we want to print on the screen, we will load into x register and a accumulator. Now let's see how they behave. Here you can see explanation or decoded instructions, and here you can see that high byte is stored into accumulator and the low byte is stored into x register. So let's say that I want to print some number that has only 8 bytes, it's just 1 byte, so it's value between 0 and 255. I would load the accumulator with 0 and then load my number into X register, and when I call this routine, the number that's stored in the X register will be printed on the screen in decimal as decimal number. And here is, let's say, do new line. So this is the routine. If we call it, it will produce the new line. Also there is set the color code, so A8CB. This will set the color. Now this is interesting routine which set the color, text color on Commodore 64, and there is all bunch of verification, compare if we can skip all of this. And one interesting part is right here. This memory address 0286 is where the color code is actually saved, and the VIC chip uses this address to get the text color. So we can just save the values into this memory address color number that we want, and yeah, the text will be in that color once it is something is printed on the screen. So yeah, now we're going to jump to a couple of examples that I've made just using these list of all these routines and using the memory map, picking some values that are interesting to use. And yeah, let's take a look at that. Okay, let's take a look at this first example that we have. So like before, first line we defined where our program is going to be stored in memory. Then our main loop is from line 10 to line 98. So firstly we are loading the accumulator with value from memory address D012. Now D012 is the memory register where the raster line counter is stored, so we are loading that number into accumulator. We are ending it with 5F hex. And on line 22 we have this instruction which transfers the value from the accumulator to the Y register. And then we are calling subroutine with JCR at subroutine at address F1 to F. Now let's take a look what that is. So here we have routine which is located at F1 to B, which says display control IO message if in direct mode. So firstly we are testing the message mode flag, and then we are exiting if control message is off. We want to skip that. Now we are skipping this and we are jumping at this memory address F1 to F, and here is the little procedure or routine that displays the error message on the screen. By pushing the value from the accumulator to the Y register, you will see here Y, because this subroutine uses the Y register as index register, right? So by pushing the kind of random value here, we get random messages. So let's go back here. What else do we have? Now, again, after we call that routine, we are storing the value of accumulator into memory address 0286, which is the memory address where we define the text color. So that means that we are going to print the error messages on the screen, and it should be in different colors. Again, we are calling the subroutine to check for a break or stop or break, right? And we are looping in case that stop key has not been pressed. We are constantly looping. So let's assemble this and let's run it. And this is what we have. All kind of error messages, well, displayed on the screen, just a bunch of text. Yeah, and of course we can stop it and list it right here. Okay, here we have another example. Let me assemble this example and then run it, and then we will explain how this works. Let's assemble it and run it, and here we go. So this is the example that you saw in my at the beginning of the video, like in intro. So what do we have here? Firstly, we are loading the X register with 00. Now 0 here will be used for the color, and you can see that color that we are printing out on the screen is black, and the color code for the black is 0. Again, we are loading the accumulator with fixed value. Now this fixed value is 4C in hex, and then we are ORing that value with the value from memory address D011. Now let's take a look at D011. Okay, D011 is the screen control register, and it has a couple of different things defined in that memory address. So current raster line is here, raster line to generate interrupt, text mode, extended background mode, screen off, complete screen, screen height, vertical raster scroll, and so on and so on. So all of these different configuration parts, and we're using the value, whatever that value is. We are ORing the value, whatever it is, in the accumulator, and that is 4C in hex. We are ORing it with D011, and then we are calling this subroutine that is located at memory address EA13. Now let's take a look what EA13 is. So EA13 says print character A and color X. So that means whatever we load in the X register will be used for the color code, and whatever we load into accumulator will be printed out as character on the screen. So that's exactly what we did. We defined 00 in X register, that color black, and our character is defined in accumulator. Now the problem with this routine is once the character is printed on the screen, there is no the cursor doesn't move into next position, so the pointer where on the screen will not move to the next position. We have to do that manually. For that reason, we're calling second routine on line 45. It says JCR AB3B. Okay, let's take a look at AB3B. Now AB3B says print space or cursor right, exactly what we need. So after we are calling, after we call that subroutine to print the character from the accumulator in the color black, and then we call this subroutine to move cursor to the right so that we progress on the screen. And yeah, that's basically it. And everything else is just like before. So let's run this one more time. Yeah, very interesting kind of 3D effect that we have here. Okay, another example. So let's assemble it. and let's run it and see what do we have. Now this is a very cool effect that we have. You can see that our characters, our random characters, are changing color. They're moving up to the screen. Some of those are moving faster and some of them are moving quite slower. It's like they are sucked up by the top of the screen. It's very nice effect. So let's take a look how that happens. So again, it's a similar or basically the same construction. So we have single loop, we are constantly looping. And okay, so firstly we are loading into X register value from memory address A1. And after that we are loading the accumulator with value from memory address A2. Now these two addresses are addresses which are located at 0-page memory. That means that we don't have to write those two leading zeros. Well, you could, but this saves lots of space and speed, of course, because I could write 00A1, that's actual address, but we don't have to write those zeros. So these addresses A1 and A2 are part of our timer or Jiffy clock, right? And that TI timer or Jiffy clock is 24-bit number, and 24-bit number is written like in form of a 3 bytes. Less significant byte is located at memory address A2, then the middle one is at A1, and the high significant byte is located at A0. Now you can imagine that this A2 value is iterating or looping from 0 to 255 quite fast. A1 value is also changing, but much slower, and A0 again even slower. Again, we are using the subroutine which is located at AI 13, which is printing the character on the screen with color. So the character is loaded into accumulator, the color is loaded into X register. After that, we are using again subroutine to move the cursor to the right, and then we are ORing whatever we have in the accumulator. We are ORing that with value D012. Now again, D012 is the raster line number, and then once we did that, we are transferring the value from the accumulator into X register. Why we do that? Because we are now going to call this subroutine, which is located at E9FF. So let's take a look at that subroutine. E9FF routine says clear screen at line X. That's the reason why we move the value from the accumulator to the X register. Now whatever number it is in the X register should represent the line number, and that line will be cleared. And this is the routine that does just that, and this is how we get that effect that suck up the characters up. So yeah, everything else is just as it was before, scanning for the stop key and ending in case that we did hit the stop key. So let's run this one more time, and here we go. Yeah, very nice effect. And the one thing that's interesting with this little effect is let's change the character that we are printing on the screen. Let's put it into, let's define some fixed value for that. So the value that we're going to use is for the hex. So that's the only change that I'm going to do. Everything else will remain the same. So let's assemble this one more time and let's run it. And what we have now is the rain effect. Yeah, kind of rain effect. It does look a little bit like rain. Yeah, so now we have a rain. Okay, so let's see what do we have here. So let's assemble this and let's run it. Now this is a little, does look a little bit broken. It's not, it's just the effect that we have. Now, yeah, I can safely exit here as well. Now let me explain what the hell this is. First of all, I will start to explain from the line 35. Now it says calling the subroutine E097, which is a subroutine that generates the random number, pseudo random number. Now, why do we have it here? We don't basically even use that. Now this subroutine is called simply to waste some time, to slow our code down. So what I will do is remove this line and assemble it again or compile it, and we will see what shall we get here. So let's list it without the line 35 assemble, and let's run the same code one more time. And this is what we have. So the only purpose of that subroutine, why it was called, is just to spend some additional time to slow our program down. Once that line is removed, now we have just clear program doing exactly what it should do. So firstly, again, we are loading the accumulator with value from memory address D012, which is again raster line number. And I mentioned before that we're going to use that a lot. This will give us a kind of randomness. So yeah, to make things interesting. And then we are ending that value in the accumulator with decimal number 7. So we don't want any number bigger than 7 in this in accumulator. And then we are transferring or moving the value from the accumulator to the X register. Now on this line 30, we had before, maybe in first example, I explained this increment the value that's stored in the memory address by 1. It's same like before, except we have this we use X register here as well. Now this X value in the X register is used as a index or offset if you prefer. So that means that you're going to increment the value in memory address starting at D011, and depending on the value of the X, if X is 0, then we will increment this memory address. If X is the 1, we are going to increment the memory address D012, and so on and so on. So we have a range of memory addresses or array that we are incrementing depending on the value of the X. Okay, again, same thing. We are testing or checking whether or not we stop, hit the stop key. We are looping here in case that we didn't, in case that we did. Now before we return back from the subroutine, we are calling one more subroutine which is located at memory address E5A0. Now let's take a look what the hell that is. E5A0 says initialize the VIC chip. Now why the hell do we do that? Well, those memory addresses from D011 up to D018, it's some of the big 2-chip registers which define the graphical mode and all sort of things, scrolling of the screen and so on and so on. So we are incrementing those memory addresses. That means that we are kind of messing up with configuration of the VIC chip, right? And to return back to the normal, we need to call this subroutine to reinitialize the VIC chip with default values. That's part of the routine that is actually executed once we power up the Commodore 64. So we are calling it to get back to normal, right? And then after that, we are returning back to the from the subroutine or back to the basic command line. So yeah, one more time. Lots of mess, as you can see. Our screen is moving left and right. All sorts of things get activated. But once we hit the stop key, everything is back to normal. Yeah. So there you go. Okay, let's see what do we have now. Okay, let me explain what this is, then we will run it. So here at line 20, there is a new instruction for us. It's called CLC, which means to clear the carry flag. We need to clear the carry flag before we start our operations. And then we are implementing exclusive OR on the value, whatever it is, in the accumulator with value that's stored in memory address D012, again raster line number, and then we are ending this with hex 01 or decimal 1. It's the same number. Now after this line 30, when we end this with 1, in the accumulator we can have two values, either 0 or 1. That's it. Now we're using the instruction ADC, which is the instruction that will add the value to the accumulator, whatever the value in the accumulator is. ADC instruction is it's actually called add with carry. Now what that means, add the value that we specified here, but also if carry flag is set, it will add additional 1. That's the reason why we clear the carry flag. We don't want that additional, possibly additional 1 if something is activated by calling all of these subroutines here. We want to be sure and clear the carry flag. Here we have either 0 or 1 in the accumulator. We are adding to that value hexadecimal value CD, and then we are simply calling this FFD2 subroutine, which is the subroutine to print the character on the screen. And then again the same thing, we are calling the subroutine to scan for the stop key, and then looping if the stop key isn't pressed, and everything else is basically the same. Now let's assemble this and see what shall we get. And here we go. It's a maze. It's 10 print maze. Of course we can do quite a bit more here, so let's add line 35 and store the value from the accumulator. I'm going to store that value at memory address 0286. Now this memory address is where the color text is defined. So, and let's list this program one more time. Now our new line is here, new instruction, and we are storing the value from the accumulator. At this position, the value in the accumulator can be either 0 or 1. That means that we are expecting when our 10 print maze is generated on the screen, some characters will be black, some of them will be white. So let's assemble this and let's take a look, and here we go. We have black and white. Now I don't want this line here. Let's remove it. Line 50 and 60. So let's okay, let's use the X register. Why not? It doesn't really matter. So we'll load the X register with value DO12. And then on line 56, we're going to store the X value at memory address 0286. So now it's not going to be black and white, it's going to be whatever the value did we pick up in this moment when we load the value from the memory address D012. So let's see how our program is looking now. So we have two new lines. Okay, let's assemble this. Let's run it, and we have a bunch of colors. Yeah, here we go. And of course we can stop it, and you can, as you can see, we stopped at a yellow color. Now we have yellow text. Yeah, that's cool. Okay, now we have this example, which is a little bit longer, so it has a couple of more lines of code. Let me explain quickly these instructions. That's from line 50 up to 60. So let's list 50 to 60. So these three instructions are kind of working together. So we are loading in the accumulator value from the memory address A2. Again, that's the GP counter or TI variable, time. And that is the lower byte. CMP is to compare. Now we are comparing that value with hexadecimal 30, and then we're using the new instruction that's called BCS. Okay, let's take a look at this compare instruction. So if the accumulator and the compared value are equal, then the result of that subtraction is 0 and the 0 flag is set. If the accumulator is equal or greater than the compared value, the carry flag is set. So that's how we know whether that value is equal to the number that we are comparing to or it's bigger than that value. And then we have our instruction that we use BCS, which says branch on carry set. So that means that we are going to jump to the label next in case that the value in the accumulator is bigger than 30, hexadecimal 30. That's it. Very simple. Let's take a look at a couple of subroutines that we used here, like this one, A50C. So let's take a look at that. Okay, subroutine A50C is actually the second line in the subroutine that read or sets the X and Y cursor position. So we are using this firstly to skip this detection. There is the same routine that reads and sets the cursor position. Now all we want to do is set the cursor position, so we are skipping that first instruction and we are jumping here A50C and we are positioning the cursor at certain position. So that's the subroutine that's used for that. Okay, the next instruction that we used is E975, which is right here. It says scroll the screen, and that's part of this open up space on the screen routine. We are jumping here and we scroll the screen. So we are scrolling the screen downwards. And we are using the subroutine also to set the cursor at the 00 position to the home. So we have a routine that does that. So we are using that as well. Okay, let's try to assemble this piece of code and see what do we have. There you go. Part of the time we are going scrolling downwards, and then we scroll a little bit upwards in opposite direction, and then so on and so on. Now the amount of time that scrolls downwards or upwards is defined with that comparison with the hex number 30. So from 0 to hex 30 we are going upwards, and everything else we are going downwards. So you're simply using the time variable, and that time, as it progress, part of the time is going upwards and some of the time is going downwards. That's basically it. So very nice and cool effect, and of course we can stop it, list it. Let's run it again. Okay, this is the last example. It's a little bit longer. It cannot fit on the single screen, unfortunately. The reason is we are working with sprites, and first part of the code that you see here is just filling the sprite memory with FFs. So we are expecting the full, like, small boxes that you will see on the screen. So Yeah, let's assemble this code and see what do we have. And here we go. Also, I don't know if you can hear this. Oh, I hope that you can hear the music now. Do I hear the music? Yeah. Of course, we should be able to stop this and get back to normal mode. Okay, so this is all that I have for you today. I hope that you enjoyed this little journey through assembly language and creating all these lovely effects. Yeah, and until next time, goodbye.